This call is now being recorded.
So let me share my screen and uh, okay, so what I will do is I will briefly go through what we have discussed yesterday, and then I will go through the circuit implementation part of the this quantum Fourier transform, and then we will go through the Qiskit implementation of this quantum Fourier transform. So for next 45 minutes, we'll do the theory thing, and then after that we will go on to the Qiskit implementation of this quantum Fourier transform. So just to recall that what we have as the quantum Fourier transform. So we have this basis J, and the quantum Fourier transform it to this superposition of some a superposition of basis. Let's say we can tell this one, we can name this one as J tilde, which is equals to 1 by root n. So it's a superposition of the k is from 0 to n minus 1. And similarly, also we define the unitary transformation, the unitary matrix for this quantum Fourier transform, which is this summation over G equals to 0 to n minus 1. And then we have here this one outer product with J. So this is the unitary transformation for the QFT. So using this unitary transformation, if we want to write the quantum Fourier transform of a general quantum state, so let's say we have this quantum state which is x, which is written as summation over x, summation over j equals to 0 to n minus 1 xj j. Then using this unitary matrix we can get, so we will apply the uqft and we will get the state in the Fourier basis as summation where this yk is equals to 1 over root n. So this is the yk. So this is what we covered yesterday. And now, uh, I will do the same thing here. So here this x and all this thing. So we can see here this basis. They are written in the form of this decimal. So it is here 0, 1, 2, 3. So it's written in the form of decimal. So now what we will do is we will try to derive the state in the form of binary representation. So how to apply this quantum Fourier transform on the binary representation of this state. So this one is 0, 0, and let's say this one is 0, 1. Then this one is 1, 0, 3 is 1, 1. So now we will do this kind of binary transformation and try to see how does the output looks like when we apply this quantum Fourier transform. So we are doing this because we represent all these quantum states in the binary form, not in the decimal. Uh, when we do the implementation, the Qiskit implementation, or even for the practical purposes. So here is the thing. So we have the, so we'll consider the n, the number of qubits is some 2 raised to n, and all the orthonormal bases, which is this x, can be written as in the binary form. So this x1 till xn, and all this xi's are belongs to from 0 to 1. So we will do here. So we will have this unitary matrix, and then we have the state x. We will apply the unitary matrix. So omega is the, so omega is so omega xyn. So omega xyn is nothing but this exponential 2 pi I xy by n. So I just use the shorthand notation for this. So this we apply the unitary matrix on this quantum state x, and then we will get this 1 by root n summation over y n minus from 0 to n minus 1 omega n xy and then y. So now we'll expand this omega xy n. So this is nothing but this exponential 2 pi I xy divided by 2 raised to n, because we have taken n equals to 2 raised to n. So now we will write, so here we will do the binary transformation for this y. So let's recall that so if we have some number, let's say decimal number, let's say 5, so we can write this one as 2 raised to 2 into, so it will be 1 into 2 raised to 2 plus 0 into 2 raised to 1 plus 1 into 2 raised to 0. So this will be 5. So generally any number, let's say if we have a number y, then we can write as 2 raised to n minus. So let's say we have a representation like this, y equals to y1, y2. So this is what the representation we are considering. So the MSB is 1, MSB is not n. So this one is the MSB most significant digit. So we will write y equals to, and these all y's are 0, 1 binary. So this will be 2 raised to n minus 1 y1 plus 2 raised to n minus 2 y2, and similarly it will go up to 2 raised to n minus n yn. If we try to write y divided by 2 raised to n here, so then this will come as y1 by 2, y2 by 2 raised to square, and similarly this will come yn by 2 raised to n. So this is kind of like we are doing this fractional binary notation. We are dividing by 2 raised to n also, and then we are writing, because we have this here 2 raised to n. So after doing all this, so we have 2 pi x here, which is same as above, but instead of y by 2 raised to n, we are writing this summation over k equals to 1 to n yk divided by 2 raised to k, because here this one is nothing but k equals to 0 to k equals to 1 to n yk by 2 raised to k. And we also now expanded this in the form of binary, in the form of this binary notation. So we have this y1 to yn, and this one is the binary representation of this y by 2 raised to n. Now I am taking the summation out of this exponential, and it will be the product, because e of x plus y is equals to e of x, e of y here for any real number xy. So we take out the summation outside, and it will be product. And now what we will do is, so let me erase this part, because there are few more steps that are involved here. Then we will write that. So 1 by root n. So we will expand this one also, the y equals to 0 to n minus 1. So we will write this one as y1 equals to 0. So we will write here y1 belongs to 0, 1. And similarly y2 belongs to 0, 1. And up to yn belongs to 0, 1. And this will be just product pi equals to k1 to n e raised to 2 pi x yk by 2 raised to k, and we have y1 tensored with y2 and all those tensored with yn. So let's consider the first one, only the y1. So we have this y1 belongs to 0, 1. We will have this pi equals to k to 1 to n e raised to 2 pi I xy k by 2 raised to k, and then y1. So here also this y1, we'll just consider the y1 for the first part. So this will be, so we have here 0. So when we have 0, so yk will be, so we'll consider only for one part. So this will be e raised to 2 pi I xy1 by 2 raised to 1. So we will consider, so we will have this y1 summation over y1 belongs to 0, 1. So this will be, you have 0 and then plus e raised to 2 pi I x by 2, and then this will be 1. So basically what we are doing is, here we have this case product. So here we have this k products. Sorry, not this one, is the n products. So each of the terms we are giving to y1, y2 and yn. So n terms are divided into these parts. So for y1 we are just taking the y1 part, and if we expand, if we try to write this summation here, so this will come as 0 plus e raised to 2 pi I x divided by 2 and then 1. Similarly, for others also, we can just write like this. So we have yi here, and then 2 raised to I here, and then this will be the yi. So this will come as something like this for each part. So, so thus what we get is 1 by root n, then tensor from k equals to 1 to n, and then this summation 0 plus e raised to 2 pi I x by 2 raised to k 1. So we can write this one, we can expand this one. So just for the sake of clarity, so this will be 0 plus e raised to 2 pi I x by 2 1. So this is what we got here also when we have this I equals to 1, and then tensor product with 0 plus e raised to 2 pi I x by 2 square 1, and similarly it will go till we have this n e raised to 2 pi I x by 2 raised to n. So this is uh, what we get after applying the quantum Fourier transform, the unitary matrix on I state on the orthonormal basis basically. So on the orthonormal basis, which is represented in the binary form. So this is what we get here. So now this will be actually useful when we do the circuit implementation, and the basic derivation for the circuit comes from, the motivation comes from this structure. So we have the tensor product here, and each term here is summation of superposition of 0 and 1, and there is some phase also in the 1. So now we will do the circuit implementation part here. So for the QFT, we need basically two gates. So one will be the Hadamard. The first will be the Hadamard gate, And the intuition of using this Hadamard gate, we can easily understand from this last lecture, that for this one qubit case. So when we considered yesterday for the one qubit quantum Fourier transform, then we saw that this the unitary matrix for this Fourier transform, for this one qubit Fourier transform, is nothing but the Hadamard operator. So from here, the use of the Hadamard basically comes. The use of the other gate. So the other gate is a kind of controlled rotation, we can say, uh, in some form. So if the other one is controlled, or you can or we can say also it's a controlled phase. So it's controlled rotation. So it has some structure, and that structure basically comes from this part. So how we can add this e raised to 2 pi I x by 2, or any like any this function. So e raised to 2 pi I x by 2 raised to I, how we can add that. So let's start with the action of the Hadamard gate on the state xk. So we have this H Hadamard, and which is xk. So which is nothing but 1 by root 2. So xk is the binary 0 or 1. So we will get 0. So it will be like this. If you have h of 0, so this will be 1 by root 2, 0 plus 1, that is the plus state. And if we have h 1, then we will have 1 by root 2, 0 minus 1. But we can in general we can write like this also. Just let's say a simple x, just a general one. We don't know about xk, but in a single form we can get somehow either of these two states. So 1 by root 2, 0 plus exponential 2 by I 2 xk 1. So here we can verify this one. If we have 0 here, the whole exponential will be 0, and then we left with 0 plus 1 by root 2, and this is what we have here. And if we have 1, xk equals to 1, then this will be pi. So pi will be minus 1. E raised to pi, I pi is minus 1. So we will get, we'll left with 0 minus 1 by root 2, and this is what this one is. So we are writing in this form just to correlated with the form which we got here. So that's why we are writing in that form. So this is the this is like the Hadamard operation working or acting on the state xk. Now we'll see how the rotation operator works here. So we have this unitary, which is unitary rotation, and we are also indexing it with k. So just for some specific purpose, just for purpose, because here we have this k kind of dependency. So with the index, so that's why we are also writing the u rotation that acts on the kth bit, we can say. So u rotation is 1, and then 0, 0. So exponential 2 pi I by 2 raised to k. So this is what the u rotation is. And from using this u rotation, we will now create a controlled rotation operator, controlled rotation on the kth qubit. So that will be I 2 cross 2, 0, 2 cross 2, 0, 2 cross 2. And then we have this u rotation, which is also 2 cross 2 op operator. So this one is now 4 cross 4 actually. So this one acts on 2 qubit. So Hadamard and U rotation acts on 1 qubit, but this control rotation works on 2 qubit. So we have this one now. So let's see how this rotation works. So let's say we have this C rotation, and it acts on the kth qubit. And here, so let's say we have 2 qubit state. So let's consider our 2 qubit state is xi xj. So if we consider C rotation acting on xi xj, so two cases will be here. So if C rotation k acts on 0 xj, so then we will get 0 xj. And the second case is C rotation k 1 xj, we will get exponential 2 by I 2 raised to k xj 1 xj. So I think it's fairly clear here that why we got this one. But let's say if we have, so C rotation is C rotation is a matrix, right? So we have this I here and we have this U rotation here, and our state is a four-dimensional state. So we have something, something, something here, four-dimensional. So the state can be anything, like this one is 0, 0, this one is 0, 1, this one is 1, 0, and this one is 1, 1. So if we have any 0 xj gate, so we can have, so we will have either one here or one here. So if we have one here and here, so it will, the I will act on that. U rotation will be, there will be no action of the U rotations. So we will just simply get 0 xj. So this one is like 0, 0 will get, or 0, 1 will get. So this is what clear from here. But let's say if we have the other thing, 1 xj, so this one will be 1, or either of these two will be 1. So then I will act on the first two part, which is 0. So there is no action on the of the I, but U rotation will act on this one, either of this one. And then we will have here this 1 or 0. So if we have xj as 0, then we'll simply left with 1, 0, because U, the first diagonal element of the U is 1, so we are just left with 1, 0. But if we have both as a 1, so then we are left with 2 pi I by 2 raised to k. So this is the action of this controlled rotation. So now the circuit for this QFT will look like something like this. So we will prove also uh, whether the circuit is valid, but let's say we claimed this one, that the circuit for this QFT will look something like this. So we have this Hadamard here, then we have this controlled rotation, this part, then this one is also controlled rotation, and this one is also controlled rotation. So this one, we apply the Hadamard, then we apply the controlled rotation for with the control on the x2. So here also this one is actually control, the this one is control, and the second qubit is the target. So this is how this control rotation is defined. So here this one is control and the above one is target, and always the x1 is target here, and the control goes from 2 to n minus 1. And so we have this n minus 1 control rotation and a Hadamard. So you can consider, you can see Hadamard is also kind of U rotation, sorry, a controlled rotation 1. Hadamard is also something like that. There is no control, but you can just understand like that. So now we'll see that whether this is actually working or not, what we want. So we want this expression here, whatever we got here. So we want the same thing. So what we, so we need this expression. There is summation 1 over root n. So we need this 1 over root n, and then tensor product with k equals to 1 to, and k equals, yeah, k equals to 1 to n 0 plus exponential 2 pi I x by 2 raised to k 1. So this is what we have to show. So let's start with this circuit and see what it does. So yes, so let first write this n qubit state. So we have this n qubit state x, which is written as x1, x2, xn. So just to recall that this one is MSB, the most significant digit, and this one is the LSB, the least significant digit. So now the first step is we apply the Hadamard. So this one is the Hadamard. We apply on the x1. So when we apply the Hadamard on the x1, so what we will get, so I'm not writing H tensored I. So it kind of like understood that we are just applying H1 on the first qubit, not the other rest of the other. So we will get 1 by root 2, 0 plus exponential 2 pi I x by 2, 1. Sorry, this one is x1 and then 1. So you'll have the tensor product with x2, x3 up to xn. So in the first step, we are only applying the Hadamard on the first qubit. Then on the second step, we are going towards this second qubit also, qubit 2. So we have this U rotation. So we have this control rotation operator that is acting on. So target is, yeah, we can say Q1, maybe like I am just writing Q1 as qubit 1, and control is Q2, which means qubit 2. So then when we apply this one, so our state will be, so 1 by root 2 and then 0 plus exponential 2 pi I by 2 x1, and then we will have exponential 2 pi I x2 by 2 square. Then we will have 1 here, and then this will be closed. So we will have now x2, x3 up to xn. So how this come, let's try to understand that. So x2 goes with 0. So there here like it will be two things, 0 and then x2, and then here there will be this exponential term and then 1 x2. So when this u rotation acts on this part, so we saw here that this will remain 0xj, and when it acts on this 1xj, so we'll get this exponential time something, and then the here the divisor in the in this denominator, so we have this 2 raised to k. So here we applied the control rotation 2, so we have this 2 raised to square here in the denominator, so this will just goes with exponential 2 pi I x2 base 2 square, and there are some other exponential terms before, and this will be 1x2. So this is what we wrote here. So we have exponential, this one comes from the previous one, and this one is 0, just remain as it is. And then we have x2 here, just take out the x2 from both of this summation part because it's common. So this is how we got this expression here. So now let's apply the control rotation. So similarly, if we apply like as we go on and we apply this control rotation 3, control rotation 4, and so on. So after applying this control rotation n, so what we will get is, so it's fairly, uh, we can easily guess here. It's simply 1 by root 2, seeing the structure. It will be 0 plus exponential. So these are the product of exponential. So I can take the power inside and do the summation. So it will be 2 pi I by 2 x1 plus 2 pi I by 2 square x2, and it will be 2 pi I by 2 raised to n xn. So this is what we get. But here this 2 pi I is common to each of these terms. So we will do like this. So we'll write 2 pi I, and then we will write this x1 by 2, x2 by 2 square, and similarly up to xn by 2 raised to n. And then we have this 1 here, and we will get x2 till xn. And this also we saw earlier that this one is nothing but x by 2 raised to n. So earlier we saw here, yeah, this one for y, but similarly just replacing the variable y with x, we get this binary. So this one is the binary form of x by 2 raised to n. So that's why we can write this one. That's why we can write this x by 2 raised to n. So this one is 1 by root 2, 0 plus exponential x by, so it will be 2 pi I x by 2 raised to n, then 1 tensored with x2, x3, xn. So this is what we got after applying these block. So if we apply just the first block, so there are many blocks like this. So the blocks acts like this one. So you have the Hadamard, you start with the Hadamard on the first one, and then you apply the control notation on the rest of the one. Then you apply the Hadamard on the second and do the rest of the qubits on do this control rotation on rest of the qubits, and similarly till we reach the last qubit, till we apply the Hadamard on the last qubit. So seeing the structure here, what we can guess is after applying, so the first block is only acting on the first qubit and it's transforming the first qubit only. And if we apply the similar kind of blocks on the rest of the qubits, so we will get this superposition for each of this qubits, x2, x3, xn. So maybe, so after applying this Hadamard and control rotation, for all qubits, like for qubits 1 to n, for qubits 1 to n. So then we will get so it will be 1 over root 2 summation 0 plus exponential 2 pi I x by 2 raised to n 1. So this one is the for the first one, and if we apply for the rest of the others, so we will get some similar to this. So this will be the tensor product. So this one will corresponds to x1. This will just not x1, but when we apply the Hadamard and the control rotation block on the x1, so this will corresponds to that part. Then if we apply the Hadamard and the control rotation on the x2, then we'll get this kind of structure here, and there will be, so the difference is only the denominator here, which is 2 raised to n minus 1. And why this is coming, because we are only, so when we are considering this second block, so we are only acting on the n minus 1 qubits. Earlier we were acting, the whole system was acting on the all the n qubits, but this one is only acting on the n minus 1 qubits. So that's why we get this 2 raised to n minus 1 here. And similarly for the last qubit, so what we will get is 2 raised to 1, because we are only applying Hadamard here for the last part, no control rotation, nothing. So that's why we have this 2 raised to 1. So this is what this is what the so just to see the structure here, what we wanted and what we have now. So so we want this one. So if we try to write this as n raised to 2n, so this will be 2 raised to n by 2, and then the tensor product of k equals to 1 to n 0 plus exponential 2 pi I x by 2 raised to k and then 1. So this is what we want. And the circuit, so we claimed that this circuit will work as a circuit for this quantum Fourier transform. So now we had to finally check that the expression which we got from the circuit is matching with what we need. So here 2 raised to n by 2. So we will just collect all the 2, and this will give 2 raised to n by 2. That's correct. And here each of the summation, so we have the 0 plus for the first k equals to 1. So we will have 0 plus exponential 2 pi x by 2. But that comes here in the last part. And if we go along, so we'll get all this terms here, 2 raised to n, 2 raised to n minus 1 up to this 2 raised to 1. The only the only issue with this one is that what this circuit gives is in the reverse order. So the qubit, the output is kind of like in the reverse order. So what we are getting here in the first qubit, so we are getting that in the last qubit here. So we have a reverse ordering here. So that's why we do this reverse operation. So we flip the first qubit with the n once doing all the operation. We flip the first with the last, and adjacency, like we will shift the opposite one, the last opposite one, and then the second last opposite one, and similarly up to the in between. So we're just flipping the ordering here. So if we flip the order, then this 2 raised to 1 will go in the first and 2 raised to n will come in the last, and then we'll get this expression what we were expecting. So this is the whole proof, and proof also we can say, and the circuit for this QFT. So just to summarize, so the circuit for this QFT contains only two gates, Hadamard and the control rotation. The Hadamard acts like this one, the control rotation acts like this, sorry, here this one, and this consists of this U rotation. Then we claimed that the circuit for this QFT looks like this, and then here we proved that indeed this is true, with some kind of caveat here that the output is in the reverse order. So that's why we applied here the flipping of the qubits. So this completes the circuit part. So maybe just for a few minutes, for 10 minutes, maybe we'll go through an example quickly for this QFT, and that example also we'll try to implement on the Qiskit. So let's quickly consider an example for this circuit implementation. So we have this 3 qubit QFT. So we have this Y3, Y2, Y1, and then we have this QFT. So we'll write like this: X3, X2, X1, and this one will give you Y3, Y2, Y1. So here, this one is most significant bit. I just changed the ordering here, but nevertheless, it will be fine. So I just changed because of this reversing of the order. Otherwise, there is no difference. There is no difference in that. So we have this. So first we will apply the Hadamard gate. So Hadamard gate on this X1. So we have this psi1. So this will be the Hadamard. Sorry, Hadamard on this X3, X2, X1, and that will be X3, X2 tensored 1 over root 2, 0 plus So this will be the action after, this will be the state after h1 acts on the state x3, x2, x1. And then we will apply the control rotation, control rotation 2, we can say here. And that will act on, so the target will be, so the target will be here, because we have reversed the order. Yeah, so the target will be x1 and the control will be x2. So once we apply this control rotation on this h after h1, x3, x2, x1, so we will get here x3, x2 tensor 1 over root 2, 0 plus exponential 2 pi I 2 square x2 plus 2 pi I by 2 x1, and then this will be 1. So this is nothing but we have pi by 4. So pi by 4, and this one is nothing but pi. So basically control rotation here is CR2 pi by 4. Oh, sorry, this one is not pi by 4, this one is pi by 2. So pi by 2 kind of thing we are applying here. Then third one is we apply the third C rotation 3. So the target will be x1 and the control here will be x3. So we applied C3, C2, H1, x3, x2, x1. So this will give you x3, x2 answered with 1 over root 2, 0 plus exponential. So we'll have now 2 pi I by 2 cube x3 plus pi I x2 by 2 plus pi I x1 at on the 1. So and this will be pi by 4. So this one is nothing but C root C control rotation pi by 4. So what how the first blocks looks like is, so we have used the flip kind of thing here. So here we have this x1, the above one is x3, x2. So we will have the Hadamard first on the H, then we will have a control rotation. So C, so control rotation of angle pi with the target with the control and x2, and then we will have a control rotation of pi. So this one is pi by 2 and control rotation of pi by 4 with the control on this x3. So this is the first block of this is the first block for the QFT. Similarly, the second block here we can apply. So the H, then there will be the control rotation. So that control rotation will be of angle pi by 2, which we can easily derive. And then finally we will apply the Hadamard here, and we will get the QFT here, the output of the QFT. And again, that will be kind of like reverse order. So we have to put the x1 here. So this will give us y1, y2 after doing here the reverse thing. So y2, y3, and this comes in the sequence like we have whatever we have. So without this swapping, so we were getting this y3, y2, y1, but after swapping we have the output in the correct order, y1, y2, y3, what we want. So this was the small description for this theory part of this implementation of 3-qubit gate. So I just here did for the first one acting on the x1, but we can do for the x2 also, and it's fairly straightforward. Just apply the Hadamard and then pi by 2, and it will change the other state, this x3. So now we'll go to the Qiskit implementation part. So maybe we'll take for a couple of minutes break, and then we'll go to the Qiskit implementation part. So now we will go through this quantum Fourier transform implementation on the Qiskit. So I have a notebook here, this Qiskit notebook. So we can go through this part now. So here, just to quickly emphasize that there is some this notation thing for the Qiskit, that the Qiskit's least significant bit has the lowest index 0. Um, it doesn't start with 1, so it starts from the 0. So it's called Little Indian ordering. So let's start this with the importing all the libraries here. So we have this quantum circuit, and for the simulation R, and then execute. So, and for the visualization purpose, we have this histogram and other things. For the numerical calculations, we have this numpy here. So now in this cell, so this cell actually contains the QFT function. So how we will write the QFT function. So here from the circuit, uh, what we had is, if we recall, that we have the Hadamard, and then we have this control rotation sequentially up to this n qubits. So for the first block, so we have the Hadamard on the first qubit, and then the control rotation with the control on the second qubit, then the control rotation with the control on the third qubit, up to the n minus 1 times, where the control rotation, the target is the x1 and the control is on on the xn. So this is what we are trying to do here is, so we are applying the Hadamard gate to the most significant digit, And then using the for loop, so we are applying all this controlled phase. So controlled R is the controlled C wrote, controlled rotation, whatever we wrote. So that is just a control phase. So that's why we have here control phase, and each of the phase is adding this pi by 2 raised to n minus the number of that the qubit index, whatever we have here. So and then so after this, so we have other this yeah QFT rotations circuit. And so here this one is the main two part that we are adding the Hadamard, and then we are adding the control rotation. So we also saw the example for this controlled we saw the example for this 3 qubit QFT circuit. And what we derived is we applied the Hadamard on the third one, and then we applied kind of like controlled phase, that is pi by 2 with the pi by 2 angle, and then we applied controlled rotation with the angle pi by 4. So this is what we are doing here. So we created a quantum circuit with 3 qubit, then we applied a quantum Fourier rotations, that is the quantum Fourier transform circuit on this 3 qubit, which is looking like this here. And this is what we got in the theory also when we derived. So this one is pi by 2 pi by 4, and then this one is the second block, this one is the third block, and this one is the first block here. So but here as we saw that the bit has to be reversed, because the quantum Fourier circuit, they actually gives the output but in the reverse order. So here in this cell, we are creating a swap operation that swap the registers. So it's just like you swap these two ones with the qubit and the last one. So corresponding. So if you are on the second qubit from the top, then you swap it with the second on from the last. So this is what it is doing, the circuit swap. And we are doing for all of the half. So that's why we have this n by 2. Once we reach half of the circuit, then already the whole circuit is now swapped. So this is now the complete QFT operation we have. So we apply the QFT rotation. So this will take care of all the blocks there, the Hadamard and the control rotation blocks, and the swap registers will take care of the last when we do the swapping. So here in this cell, so what we are trying to do here is we are trying to find the QFT circuit for this 3 qubit case 000. And if we try to see what would the output of that, then we can clearly see that it will be just 0 plus 1 by root 2. And this is what we will get here. So let me go through the circuit here. So we applied the quantum circuit, we created a quantum circuit with 3 qubits, so Q0, Q1, Q2. The indexing in the Qiskit starts with 0, that's why we have here 0. And then we applied this QFT, the complete QFT function. So this includes swapping also. So after this after this QFT, we draw the circuit, and here this is what it looks like. So we have the first block here, then the second block here, and then the third block here, and then we finally swap the first Q0 with the Q2, and the output we'll get. So to see the output, let's use the block sphere here to visualize the output of the QFT. So we will use this all the simulations things here, the command to get the simulation results. So we will execute the circuit here using this function execute. And now here this one is what it is printing. So we get this X. This is nothing but the plus state. This one is the plus state, and this one is the plus state. And QFT of this is nothing but the plus. And this is clearly understandable because we were getting summation over 2 pi I with something 2 raised to k, and then x1, x2, x3, where here all the x1, x2, x3 are 0. So you just put an exponential of some 0 is 1. So that's why we are getting the plus state, this 0 plus 1 by root 2. So we have the first qubit also 0, and then 0. Sorry, this one is plus, this one is plus, and this one is plus. So now, so we saw the output for this QFT all 0 state. And now we'll see the output for this QFT 101 state. So we did to encode this 101, 101. So we applied this to X gate, that because we generally initialize, so this quantum circuit generally initialize the circuit with all zero states. So we have all this zero, but we apply this X gate on the Q0 and Q2. So we'll get this 101. And now we will apply this quantum Fourier transform. So again, this one is the first block, this one is the second block, this one is the third block, and then the swapping. So this is the complete QFT operation. So again, we do again all this simulation. So we will write all these simulations commands here. So these two, and then we'll print the results. And so this is the result what we will get. And then we try to see this vector, what the vector we got on the Bloch sphere. So there is not much sense from this state. It's hard to make an inference what we got, but let's try to visualize it on the Bloch sphere and try to see what is there. So the first state is actually some rotation. So if you go from this direction, uh, the that is what we call anti-clockwise. So we go anti-clockwise direction here. So we got this vector, and if we see that this one is actually a 5/8 of full rotation. So this is like 5/8. You can say pi by 5/8 pi. So the rotation here from this positive x-axis, it will be 5 pi by 8, and this one is the pi by 4, the one quadrant rotation from x to y, and this one is the pi rotation from this positive axis x. And here we have some description here what is happening for this plus plus 101 state. So the state so we started here. So this state, the decimal form of this state is 5. So what we got after the quantum Fourier transform is some 5 tilde, and that is that we can see actually from the expansion of that. So we have this e raised to 2 pi I, and then xk by 2 raised to k. So from there we can see that this one is nothing but 5/8 of Fulton, the first qubit.
Sir,
And
excuse me.
yeah.
Are you sharing? I'm not able to see your screen. Is it only for me or?
Oh, okay. So uh, I don't know. So is anyone who is facing the same problem, or
Screen is visible, sir.
Visible, no? Okay, okay, okay. I think, yeah, I'll check. Thank you.
okay? So now, how about now? Can you see?
Yeah, sir, we could see you're moving.
Okay.
Yeah, yeah, I'm able to see now. Yeah.
Okay, that's good. Okay. So this is what we can. So we have to do some kind of like analysis here just to get some more feeling that why this 5/8 is coming. But we can see that very easily by the expansion, whatever we have written just now in the last hour. So if we just put that in, put all these things, the 101 state, then we'll get the output. So this is all about this quantum Fourier transform. So I will again kind of go through it very quickly just to summarize. So here we define this QFT rotations. So QFT rotations is nothing but implementing all the blocks here. So this one is the first block, second block, third block. So we are just implementing the Hadamard and the control rotations. And then we define this function swap register. So because this QFT circuit gives you the output in the reverse order, so we will do the swapping here. And then we defined a complete QFT function here, and that QFT function is consists of two things: the QFT rotations and the swap, and then this will complete the whole QFT operation. Then here we saw what will the QFT of 000, all zero state, and then we saw here, and this one is very much clear to us because of all zero state, and all zero state will give you all kind of like plus plus plus. We also saw this 101 state. So we did the same thing as above for all zero state, but instead we applied this XX just to encode the circuit into 0 or 101. And then we plotted here, and then we got this vector. This one is some 5 pi by 8 rotation with some 5 pi by 8 rotation. This one is pi by 4 rotation. and this one is pi by 2. This one is pi by 2 kind of rotation you have. So yeah, why I actually, this one is pi rotation from here, but in the quantum you say this one is like half of the full term, and so the rotation actually is like diagonal, like it goes to half. So if we have here from 0 to 1, the rotation is pi, but the actual rotation is pi by 2. So that's why here this one is a pi rotation in the geometrical sense, but from the quantum perspective it's pi by 2. So here also this one is rotation pi by 2 in the geometrical sense, but here this from the quantum sense this is just pi by 4. And this is comes from the theory of the Bloch sphere. So in the Bloch sphere we see that theta by 2, not theta. So these things comes from the theory of this Bloch sphere, how to represent a quantum state on the Bloch sphere. So this completes the quantum Fourier transform implementation. We can also change at we can also try by ourselves by changing all this 101 to different coordinates for different basis states, all 111 or 1011, or we can also do the superposition of all these states and try to see what's the output looks like. But every time we don't have to plot this Bloch sphere, we can also plot the histograms and try to see what is coming or what is not coming. So now we will see the another thing of this. Now we'll see the other side of this Fourier transform, that is this inverse Fourier transform. So inverse Fourier transform is just the reverse operation of this quantum Fourier transform. So you get this quantum basis, let's say 5 tilde, and you apply the QFT circuit in the reverse form. So not the reverse, actually the inverse form. So generally we take the inverse of some function. So similarly, this one is again the same thing. You are taking the inverse of the function. So let's say earlier we were trying to do the x square, we have the x, and we were trying to find the function x square, but now we will do the inverse thing. So we have the x square and we will take the under root and then we'll get back the same x. So this is what we are trying to do here. So we have this 5 tilde and we apply the QFT inverse QFT circuit, and then we'll get this 5 because we got this 5 tilde from 5 by applying the QFT. So if we go in the reverse order, we'll get the 5 here. So we don't have to actually derive what's the circuit of the inverse quantum Fourier transform because we have a function in the Qiskit. So that's called this. So you just do the circuit inverse. So that will do all kind of manipulation at the this at their own like programming side, and then that will give you the inverse circuit of this quantum Fourier transform. So you don't have to do that. So we can create a circuit which is this QFT, the quantum Fourier transform. And just to recall that we have a swap also in this QFT. So we have a complete function now in this QFT circuit. And then we have this inverse QFT circuit, which comes from taking the inverse of this above QFT circuit. So we got this inverse QFT circuit, and then here we are kind of like just appending the circuits with the so we have this n qubit circuit, and we are just trying to implement this. So we are just trying to append the circuit, two circuits, inverse and the with the qubits. So let's see here what this inverse QFT is doing. So we created this quantum circuit for 3 qubits, and here in this part actually we are kind of creating the um, quantum Fourier transform of this 101 state. So that is 5 tilde, which is this 5 tilde here. So we are creating this the quantum Fourier transform version of this 101 state manually. So we are not implementing the this QFT circuit, but we know what the output looks like. So that's why we are creating this one by our own. And then this is what why we are doing this is we are doing just to see that the inverse quantum circuit works on 5 tilde and it will give you 5. So we applied this circuit here, the Hadamard and all these things. So this is just encoding the 101 into the quantum Fourier transform version of that. And now we applied again this Bloch sphere simulation and then plotting on the Bloch sphere. So we get the vector, this vector, and then the second qubit vector and the third qubit vector, and this one is similar to what we got here. So basically this encoding is correct, and whatever encoding whatever output we get is basically the 5 tilde. And then now here we apply this inverse QFT part. So inverse QFT, and the inverse QFT will look something like this here. And maybe let's spend some time here and try to infer how does the inverse QFT looks like. So we saw that the QFT has something like this. So it starts with the first block here, H, and then the phase with pi by 4, phase with pi by 2, the second block, H, then phase pi by 2, then third block, and then the swap. But now when we take the inverse, then everything is now kind of like reverse. So this this green, this pink and yellow, this pink and violet, these two blocks are nothing but the encoded form of this 5. So this is nothing but just giving you the 5 tilde. But here the main thing is, the interesting thing is here the inverse QFT. So we are not doing the inverse of the QFT, the quantum Fourier transform. So earlier we have the swap at the last, but now we have the swap at the beginning. And then the third block now comes as a first block. So we have this, the second blocks now comes as a second block because we have only 3. So second will be swapped with second. So there is no, so this one is the second block. But here also we have to just to emphasize that H is now coming after this controlled phase. So earlier we have the H first and now then controlled phase, but now we have controlled phase and then H. And also in the controlled phase, earlier we have this pi by 2, but here we have this minus pi by 2 because we are taking the inverse. So when we say inverse, so then we mean that we are taking the dagger. So we have this QFT and then we are taking kind of dagger here, and then that dagger goes inside and it will bring you e raised to 2 pi I. So when we take the dagger, so it will become e raised to 2 pi, e raised to minus 2 pi I. So that's why we are getting here minus. So this is what the second block looks like. The third block comes as a last, sorry, the first block comes as a last, and this one was the last control phase, but it comes as a first, and then this pi by 4, and then this H is coming. So this we can clearly see the how does the inverse things looks like. It changes the sign of the rotation from plus to minus. It reverses the order of the circuit completely. So whatever was coming first, it is now coming on the it is now coming last. So within we will do this. This is nothing but this is just a barrier which comes with all these circuit things. So this now we'll do the measurement on this Q0, Q1, and Q2. So we'll use this simulator and we'll execute for 1,000 times to visualize on the histogram. So what we should expect is after performing this measurement, so we had this 5 tilde, which is the quantum Fourier transform version of the 5. So we got this 5 tilde here from this encoding circuit. We applied the quantum inverse quantum Fourier transform, and then this is, so what we expect is the 5, that is the binary form is 101. So if we apply here, if we do all the simulations, so these are just the function for simulations, and if we try to plot that simulation results, the number of times we get the 101, so we can clearly see here that with probability 1, so it means that we simulated it for 1,000 shots. So for all the 1,000 shots, we are getting 101. So this is just for the simulator part. So if we try to do this, implement this on the real quantum computer, then there will be some fluctuation here and there, but most probability will be concentrated on this 101. So this actually concludes that indeed the circuit is correct and all those things we are trying to do here and is making sense to us and whatever we expected. And so yes, so this is all I wanted to discuss. So the theory thing and this quantum Fourier transform for using the Qiskit. So maybe for next couple of minutes I can take any questions and discuss the other things which I may missed or which you have anything in the mind to share and discuss. So I will be happy to discuss. Or if you want to repeat me, if you want me to repeat anything or go through anything twice again, so then I will be happy to do That also.
Nothing, sir. Hope the code will be shared. Otherwise, no problem.
Yeah, sure. So I think Srinjoy, maybe Srinjoy will take care of all those things, the sharing part.
Hello, hello, Mohammed.
Yeah, hi.
Hi, hi. Yeah. So I was just wanted to convey that if you are on Discord, then you can send all the notes and the notebooks in the Discord itself, in the
Okay, okay,
VIP
sure.
Quantum Club. So are you
Uh,
on Discord, Quantum Grad
I am
Discord?
on Discord, but I am not sure if I am on that channel.
Let me. So what is your username? Can I know your username?
Let me open. It's been a while to open Discord, so
Okay, if you could provide me your username, then I can search you and I can create an invite and send
okay,
you.
okay. Maybe you can search AAMIR Amir.
Okay, let me try. AAMIR hash 2519.
That's correct.
I added you just now.
Okay, let me see.
Can you see the channel named
Yeah,
VIT-Quantum-Club?
yeah, I can see that. Okay,
Yeah,
I'll share that.
yeah. You can share all the materials here.
Okay, sure, sure. Sounds good.
Yeah.
Okay, so we will end the lecture here then. If